looked at the external characteristics of the shunt excited DC machine. Then we had looked at the compound machines, how they will give the characteristics. One small correction I would like to put up. If you may recall, we had actually drawn the magnetization characteristics somewhat like this, and we had also drawn the field characteristics somewhat like this. So both of them, wherever they intersect, we call this as the operating point under normal condition. And we said this is EG, so this is going to be EG and this is IF. This is what we had said. And then when I plotted external characteristics, I should have taken the VT, which is actually not EG, it is the voltage across the field winding. So what we plotted yesterday was internal characteristics, that is known as internal characteristics. Internal characteristics actually talks about what is EG versus IA. IA is the armature current, which is internal current, and EG is the internally generated voltage, right? So what we had actually looked at was each of these voltages. So we looked at probably some voltage like this, another voltage like this, the third voltage like this, the fourth voltage like this, and so on. This is what we looked at continuously. And then we had plotted basically whatever was the value available. Probably if I just look at this point, this is what is IARA drop that is available. And similarly, if I look at another point like this, this is what is the IARA drop available. So if I look at these as EG naught, EG1, EG2 and so on, correspondingly I would be able to get here IA is 0, here IA will be a small value probably, so I should plot it somewhat like this. Then probably here IA is larger, so I have to take it like this, and so on and so forth. So I'm going to have continuously increasing current, and after some time I am probably going to see that even in this case IA is pretty large. Whereas if I probably look at another voltage like this, right, I'm going to have something like this. So here probably IARA drop at this point is really not as large as what I am getting here. Here it is larger, whereas here this is going to be slightly smaller. So it comes in the decreasing direction. So when I plot EG versus IA, I call that as the internal characteristics. Whereas if I plot IL versus VT, so VT versus IL is known as external characteristics, right? Whereas EG versus IA is known as internal characteristics. Please note that for this particular operating point, this is EG versus this is VT. There is a difference, right? Huge amount of difference in terms of voltage. So I am definitely going to have less amount of VT available as compared to EG, because IARA is the drop that is taking place internally. So we have shown a huge drop clearly. That is what is going towards really giving me the armature current, right? So this is actually the value which is corresponding to the terminal voltage. So the terminal voltage in this particular case, if I look at EG, it is here, whereas VT is here. So VT is going to be definitely smaller, because I'm going to have basically VT is coming as the output, which is also coming across the field. So this is RF. So I'm going to have IF RF here, and I'm going to have the load here, and I would have VT is here, and VT divided by whatever is IL is going to be RL. So this is RL. So this is IL. And IL is approximately equal to IA, we can still assume, because IF is a very, very small fraction of the overall current that is being supplied by the armature, because of the fact that RF is going to be quite large. So I can still assume at least IA is approximately equal to IL, but I can't definitely assume EG equal to VT. So that's the reason why just wanted to make this small correction. Any questions? Because I hear a lot of crosstalk. If you have any questions, please address it here, please. Thank you. So much so for shunt excited generator. I'll again recall the characteristics what we drew for the compound generator. So we said basically again we are looking at the load current or armature current, either way is fine, and I am looking at what is VT, the terminal voltage. So if I am talking about ideal characteristics, I should have had the characteristics somewhat like this. But if I am looking at the shunt generator characteristics, or separately excited generator for that matter, I will have a drop like this. So this is essentially, let us say, shunt, no series at all, no series winding at all. So this must have been the ideal characteristics. But if I am providing compensation with the help of having a series winding, which will actually increase the overall flux, because the overall flux is going to be phi shunt plus phi series, I can provide excessive amount of compensation, in which case probably the voltage will rise quite a bit. So I would call this as over compounding. Whereas I may have somewhere in between the shunt configuration and the actual ideal configuration or level compounded configuration, we will call this as under compounding. Whereas if I am having the compensation in such a way that it is almost close to the ideal characteristics, right, very close to the ideal characteristics, which will actually have the terminal voltage fairly constant irrespective of the load that I am putting on the machine, then I may call this as level or flat compounding. So these three actually are coming under the category of cumulatively compounded generator. So cumulatively compounded generator indicates that the series and shunt are always in the aiding configuration. They are going to aid each other, whereas the last one what we just said was differential compounded. So in which case it is going to fall down to zero voltage condition, because I'm going to have at some point the series field completely killing maybe the shunt flux, because of which the overall voltage that is generated itself is going to become eventually zero. So this we call as the differential compounding. So this is essentially the characteristics of a differentially compounded generator. Differentially compounded generator has only one single application, only one application, that is generally in welding. In welding, invariably, when the workpiece is getting stuck to, the electrode, then we are going to have a dead short circuit. It's a dead short circuit. So if I am having dead short circuit, still I don't want the current to go to extremely large values. So this essentially tells you the short circuit condition, right? This is the short circuit condition, literally. So in the case of short circuit condition, where I want to limit the current still, and short circuit means voltage is 0, obviously. So this really comes in handy because I don't have to put any special control for making sure that the current, does not exceed a particular set limit. I don't have to do anything. So in the case of welding generator, I can use a differentially compounded DC generator, which will work perfectly fine, especially when the workpiece and the electrode are getting stuck to each other. You will still have a short circuit condition with limited current because the voltage itself is getting really limited in the case of differentially compounded generator. Whereas all the other applications would require generally cumulatively compounded generator if I am talking about holding the voltage almost as a constant, or if I want slight increase in the voltage during the machine being loaded further and further and so on. So generator characteristics are generally drawn with the field excitation most of the times, that is the main field excitation generally is kept as a constant. We tend not to vary the IF shunt. Generally we try to keep this as a constant. Also omega of the prime mover, we try to keep it as a constant. We tend to keep these two as a constant because we are looking at the capability of the generator to generate a given voltage and a given amount of power or current when I'm holding these two as a constant. That is when I keep the excitation as a constant and when I keep actually the speed also as a constant. Please understand, the speed is the characteristic of a prime mover and I'm not testing the prime mover. What I'm testing is the generator. So I would not like to really take the prime mover characteristic into account. I would like to keep the speed as a constant at a given speed, how my generator responds. That is what is my concern. So generally when I draw the generator characteristics, I would like to keep these two as a constant. The field excitation I would keep as a constant at rated excitation. I defined already what is rated excitation. Rated excitation is that particular value of field current at which my machine will be generating rated voltage, right, with the speed being at rated speed or given speed. Whatever is the given speed, that will be at rated value. So only that is known as the rated excitation. So I'm going to keep the field current, shunt field current especially at rated value, right? Last, what we are going to discuss is the series generator, which is hardly ever used. It's hardly ever used, but just for the sake of continuity, we are going to discuss about it. And this is used as a motor quite often. Series motor is employed everywhere, but series generator is hardly ever employed. Think about it. As far as the series generator is concerned, I'm going to have the field here. And I have to connect the load here. Right? So if I don't have any load, there is no field current as well. If there is no field current, there is not going to be much of generation except for the residual magnetism. So it doesn't make really any sense to draw the open circuit characteristics of a series generator. Because if I keep it as an open circuit, that is the question of field current. If the field current is not there, I'm not going to really draw any characteristics at all. So there is no point. So that is the reason why normally if I call the series field as S1, S2, I am going to actually separately excite this S1, S2 to draw the open circuit characteristics. That is the only way out to draw the open circuit characteristics of a series generator. For that, I have to first of all separately excite S1, S2, give different values of field current and see what kind of voltage is generated across this armature. So I'm going to put a voltmeter here. So I'm going to connect a voltmeter with, plus minus DC voltmeter, of course. I will put a DC voltmeter with plus minus like this. That is essentially going to give me for different values of the field current what I am going to get as basically the voltage generated across the armature. But one thing we have to be careful is, because the series field is always connected in series with the armature, I will have RA and RF series comparable with each other. What I mean is, if I say it is 0.2 ohms or 0.3 ohms, that is what is the armature resistance, the series field resistance is also going to be only 0.2 or 0.3 ohms, nothing more than that, because it will be thick wire carrying the same current as that of the armature current, right? But what I am applying is maybe 220 volts. I may not have any other supply in my laboratory or in my, industrial environment. So when I want to conduct a open circuit characteristic test, I have to necessarily apply 220 volts. And if I am applying 220 volts to a 0.2 ohm resistance, huge amount of current will flow. So I can't afford to do that. And also please realize that this is going to have a back EMF in all probability, or generated EMF, even if I am looking at it as a motor. So if I look at the series field winding and the armature current, armature resistance along with the load resistance are limiting the current. All of them put together. So EG divided by R series plus whatever is RA plus RL. All of them are coming in series. That is what is limiting the current. So if I just apply 220 volts to the series field winding, there is nothing to limit the current properly. So I have to include necessarily an external resistance. Unless I include an external resistance, I am going to see that the series field is going to draw enormously large current. Very, very large current. So it is definitely not a viable option to connect 220 volt supply directly across the series field. So I necessarily need to connect an external resistance. So I'm going to have the current that is flowing through the series field circuit. Let me call that as IFS, series field current, right? So I can adjust this current by adjusting the external resistance, and I would be able to get an open circuit characteristics even for this. So the OCC will have IFS on one side and EG on the other side. So this is EG. What I'm getting here is EG. So I'm going to have essentially the open circuit characteristics plotted, and that will be probably somewhat like this. Right. Now, with this as the characteristic, I should be able to definitely say that this IFS compared to IF shunt might have been 0.1, 0.2, 0.3 amperes, whereas IF series will be 1 ampere, 2 ampere, 3 ampere and so on. Please understand this, because the series field will always carry armature current which is of the order of a few amperes, because the armature resistance itself is only 0.1, 0.2, and that is what is generating the power ultimately. Whereas shunt field has 150 ohms or 200 ohms as its resistance. So if I apply 220 volts divided by 200 ohms, I'm going to get very, very small current. So generally, if I look at IF shunt, it will be of the order of only 0.1 or 0.5 ampere. Whereas IF series will be of the order of a few tens of amperes if it is a larger machine. Even larger than that, it will be few hundreds of ampere. In fact, it depends upon the rating of the machine. So it is not going to be a small current. So this will be very clearly tens of amperes in all probability. Right? Whereas in the shunt field, when we drew the open circuit characteristics, you will always look at the current value to be about 0.1, 0.2. That's it. So low range ammeters will be used in shunt generator field coil. High range ammeters will be used in the series field coil, always. Right. So this is the OCC of the series generator. So now let us try to look at again the external characteristics briefly. So if I am going to have actually this as the OCC, right? This is EG and this is going to be my IFS, or I would say this is also incidentally IA later on when I am going to connect it really as a series generator. So when I connect it as a series generator, I am going to have this along with this field, and then I am going to have the load here. Right? So this is RL. This is, if I say this is plus and this is minus, I am going to have this as VT, the terminal voltage. Right? And I am going to have RA here and RFS here. So if I look at what is the drop and what is terminal voltage, the terminal voltage is going to be EG minus IA multiplied by RA plus RFS. Right? That is how it is going to be. So I should probably have that line drawn like this. I am just arbitrarily drawing a line which is actually IA multiplied by RA plus RFS. So the slope of this line clearly will be RA plus RFS. What is the series field resistance plus armature resistance together. Now whatever is left over will be only this much will be the terminal voltage. This is what is available as the terminal voltage. So this is what is VT at every point. Whatever is the difference between the open circuit characteristics and whatever is the field resistance plus armature resistance line. The difference between these two come up as the terminal voltage. So I am going to get terminal voltage at every point, right? This is VT1, maybe this is VT2 and so on and so forth. This is what I am going to get as the terminal voltage. So if I want to really plot the external characteristics, I have to say it is IA. After all, IA equal to IL equal to IF. There is no difference at all. Please note that this current is the same if I may call this as IA, or this is IF, or if I call this as IL. All of them are the same. All of them are in series. So all the three are essentially the same in a series machine. Right. So now if I actually plot how this value would be, it will be definitely less than EG. Terminal voltage will be less than EG. So it may start like this, and then I should draw. Definitely the amplitude what I am getting will be smaller and smaller. Probably I am going to have more and more drop. So because of which it might actually fall. Eventually the voltage will definitely fall. Because IA is increasing, IA multiplied by RA plus RFS will definitely increase. So what is available at the load terminal will fall eventually. So this is how it is going to be. And if I have actually the load characteristics which is IL multiplied by RL, maybe if I have IL multiplied by RL as this particular line, load line, this is the load line. So in which case this is equal to VT, that's what we are drawing. So this is IA or IL or IFS, all of them are the same. So it doesn't matter. I can write anything as my x-axis. So this will be the operating point for a given load, where the load line is intersecting with these characteristics. So this is going to be actually the VT value, right? If I have a different value of load resistance, maybe the load resistance is larger. So let me call this as RL1. If I have a different value of load resistance, maybe somewhat like this, where RL2 is the load resistance which is greater than RL1. In that case, the voltage happens to be much smaller. So as I increase the load resistance further and further, or as I draw smaller and smaller current, I'm going to have less and less voltage as the operating voltage for my series generator. Right? Yeah. It will decrease after some point, because if I look at the drop, IA-RA drop, IA multiplied by RA plus RFS drop will be quite sumptuous as compared to what I am having as the saturated value of voltage. Please remember that the voltage is going to saturate. This voltage is saturating. It is not going to increase much. So that is like a constant, out of which I am cutting off IA times RA plus RFS. No, see, until here it is increasing. Until here it is increasing. So, I am showing the increase probably until some time. After that itself it should start dropping. Yes, you are right. The flat portion will not be there much. It should start dropping. You got his question. What he is asking is, if the voltage is shown to be flat, the saturation has been, attained, then after that itself it should start dropping right away, because if the voltage is a constant, IA-RA drop is continuously increasing as my IA is increasing. So you should not have any flat portion at all. It should start dropping right away. What he means is, I should have probably drawn the characteristics. It is increasing, all right, and after that it should start dropping. Hardly ever there should be a flat portion in the series generator. That's right. Okay, so this essentially completes our discussion on the generator operation and the generator characteristics as far as the DC machine is concerned. Now we are going to migrate to motors. What we looked at so far is, I am giving a mechanical power input. Some portion goes away as friction and windage losses, which are actually corresponding to the rotational losses or mechanical losses. Friction and windage losses. As I told you, friction, all of you know, windage is due to the wind which is surrounding it, which is going to actually impede the motion, because you are not really looking at the machine running in a vacuum. It is surrounded by air. So it is known as windage loss. So friction and windage losses are mechanical losses. What is available after this is actually being fed to the DC machine. This DC machine, which is working as a generator, is actually converting the mechanical power into electrical power. That's what it is doing. And through the electromagnetic, via media. In between you are having the magnetic via media. That is what is allowing the conversion to take place. Now very clearly even this will have some losses. One of the losses that we normally see is IF square RF. In the field circuit I am going to have definitely some losses. I would not really call them as exactly core losses, because it is actually the copper loss, the resistance of the copper winding which is existing in the field. After all, I am sending a DC. So there is no question of hysteresis loss and eddy current loss in the field circuit. So I will not call them as core losses. It is IF square RF, which is the copper loss inside the field system. Then I am going to have armature copper loss. And armature might also have some core loss. So armature will have some core loss. Please understand, armature is carrying you know, a current which is alternating, which is not a DC current. That's why armature core has to be laminated. So I will have to definitely account for the armature core losses and the armature copper losses, which are actually IA square RA. Apart from that, I will have core loss also in the armature. Now what is available after this is going to come out as the useful output, which will be VT multiplied by IL. This is what is the useful output that is available in the form of the load current multiplied by the terminal voltage. That is the useful output power. So this is essentially my generator power flow, how exactly the power flow takes place in the generator. Whereas if I look at the motor, I am going to have the motor here where I have to give actually the input as maybe VA and IA. So I have to give armature voltage and armature current totally. Rather than saying IA, maybe I might like to say it is IL, because it is the total line current that I am passing into the machine. Maybe if it is a shunt machine, I am going to have some amount of current being carried by the field circuit, some of the current being carried by the armature circuit. So it is better to write this as VT multiplied by IL. Out of which, again, I will have some portion actually lost, probably as IF square RF. Some portion probably lost as IA square RA. And also armature core losses. So these will be lost definitely as some of the losses after I give certain amount of power to my machine in the form of electrical power, right? Now what is coming out ultimately is actually the mechanical power output. Now what is actually lost from here is friction and windage losses. Now what is left over finally is the useful mechanical output. So this is going to be the useful mechanical output that comes out. Yeah. Generally in DC machine, we are not going to laminate the field and we are going to always give a DC current to excite the field. So what I am giving here is also a DC voltage. This is a DC voltage and this is a DC current. Because it is all DC completely, there is no hysteresis, there is no eddy current. Eddy current and hysteresis will show up only if I am going back and forth in terms of the flux, or if I am traversing the hysteresis loop, which never happens in a DC machine's field system. Armature, you are having AC, right? Commutator and brushes we put only because what we are having inside is AC. What comes out is DC by the split ring. So what is inside is AC, so it will have hysteresis losses, eddy current losses. That's why we wrote armature core losses. So armature will have core losses, whereas field will not have core losses. Right? So this is going to be the basic power flow diagram as far as the DC motor and the DC generator both are concerned. So when we calculate the efficiency, finally we will say useful output. Whether it is mechanical or electrical is a matter of detail depending upon whether I am talking about the generator or motor, divided by total input. This is what is the efficiency. So the efficiency will be calculated based upon the total input I am giving and what is the useful output I am having ultimately. And the ratings are generally given in the form of whatever is the useful output. So if I am given for a DC machine, it is a 2.2 kilowatt machine. 2.2 kilowatt indicates the useful output that will come out. But when I am giving the voltage and the current, the rated current and rated voltage, if it is a DC motor, that indicates the input, obviously. If it is a generator, that indicates the output. Right? So voltage and current, when I specify very clearly in a motor, it is going to indirectly talk about the input. Right? So let us now try to, with this background, let us try to look at the DC motor configurations. So let me start out with separately excited DC motor. So I have a separate excitation for the DC field winding. So this is going to be my armature. I am actually connecting a voltage supply which is VA. Let me probably say this as positive, this as negative. So I am inputting a current in this direction. Let me call this as IA. The field is separately excited, so I am going to have the field connected to a separate source, probably with a field resistance as well, which is a variable resistance. So this is our external, and this is going to be IF. And what I am actually connecting here is VF. In all probability, in the laboratory and all, I am going to have VF and VA to be almost of the same value, 220 volts or whatever. So I will, as a rule, have RF to be pretty large, because of which IF will be only of the order of 1 ampere or less. It's going to be really, really small. So RF basically will be very large. So I'm going to have VF divided by R external plus RF is equal to, IF, whatever is the field current. Right? Now, I am going to have this IA passing through this, and of course the load is now coupled to the shaft of the DC motor. So I'm going to have a mechanical load coupled here. Yeah. In case I want to reduce it further for some reason. If I want to reduce, let us say, the current further for some reason, we will look at speed control, where we will see that we might play around with the field current a little bit in a DC motor. Right? Please understand that IF is going to be somewhat proportional to the flux. So if this is proportional to the flux, the torque is proportional to phi multiplied by IA. This is what we said. So I can say indirectly this is approximately equal to some constant multiplied by IF multiplied by IA. So if I want to adjust the torque, I might like to adjust my field current or armature current, as the case may be. So whenever I want a torque control, I might adjust my armature current or field current. Right? So this essentially tells me there is some kind of control operation I can incorporate into the DC motor to arrive at the required value of torque, required value of current and so on, required value of speed and so on. One more equation we wrote for the DC machine in general is E is proportional to phi multiplied by omega. So I can write this to be approximately equal to K times maybe IF multiplied by omega, which indirectly tells me maybe I can have a control over the speed by adjusting probably the voltage, which is actually the back EMF. In this case, it's not really applied voltage. Let me now try to write the electrical equations. These are some of the equations we already knew. Let me try to write the electrical equations. We wrote one of the electrical equation already. right? Now I should be able to say VA equal to clearly IA times RA, but I will definitely have a back EMF induced whether I like it or not, and back EMF by virtue of following Lenz's law, it has to definitely oppose whatever is the original voltage. So I should have the back EMF actually having the positive here and negative here, so that they are not in series addition, they are in series opposition. So EB and VA are going to be in series opposition. You think about it, you have basically a conductor sitting inside the armature. I have applied a voltage, right? When I have applied a voltage, it is going to carry a current, in all probability an enormously large current, unless I limit it. So it is going to carry a large current and it is going to generate a torque. Because of the torque, it is going to start moving. When it is moving, the same conductor, which is actually sitting in a magnetic field and it is moving, will have an induced EMF. And that induced EMF we call as the back EMF or counter EMF. That counter EMF cannot be dominating over the applied voltage. If it is dominating over the applied voltage, the entire action of the machine is killed. That's it. It's not going to have any current, right? So necessarily that voltage is slightly subdued or less than whatever is the applied voltage. So that is less by what amount? That will be less by IARE. So I'm going to have VA equal to EB, which is actually working like a voltage source which is opposing the applied voltage. So I'm going to have VA equal to IARA plus EB, or on the other hand I can write EB equal to VA minus IARA, which I can again write this is some KIF omega or K dash phi omega, right, which will be equal to VA minus, I can write IA as torque divided by K phi, right. So let me write this as torque, electromagnetic torque divided by K phi multiplied by RA. This gives me the torque speed relationship of a separately excited DC motor. So this is the governing equation for the torque speed relationship of a separately excited DC motor. So this is essentially the important relationship for a machine which is working as a motor. Yeah. Okay, K dash, fine. I can write this as K dash. Thank you. So this is the back EMF constant or torque constant. That is K dash. So I should be able to write now the equation as omega equal to VA divided by K dash phi minus TE divided by K dash phi the whole square multiplied by RA. So this gives me the torque speed relationship for a separately excited DC motor. And if I want to keep the flux as a constant, because it is separately excited motor, I have a complete control over the field current that I am passing. It is an independent supply. If I assume that I am keeping it at rated value, the flux or the field current at rated value, this is going to be a constant, this is going to be a constant. Right? So I can directly say by adjusting the armature resistance, I should be able to get a speed whatever I want, probably, right? Given the voltage, given the torque, and so on and so forth. I am just giving you an example. Let us say a DC motor is driving our elevator, right? Maybe 5 of us have gotten in, which means the torque is a constant. The torque to be developed by the machine is fairly a constant. So I can try to run the machine at whatever RPM or whatever speed I want, provided I actually adjust my armature resistance, or externally I can include a resistance in the armature circuit. So along with this, if I want, I can always include a resistance in the armature circuit. If I include a resistance in the armature circuit, that will actually modify this equation to RA plus R external. So the moment I include a resistance in the armature circuit, I am going to get clearly, a variation in the speed while developing the same amount of torque. Right? So this tells me basically I will be able to adjust the speed by adjusting the armature resistance, external resistance. Internal resistance, I can't do a thing. It is set in stone. So I can include an external resistance to bring down the speed. That is possible, because it will only bring down the speed at a given torque value. So this tells me that speed control is possible by adjusting armature external resistance. Right? So this is one of the speed control methods which we will talk about eventually. Right? So this is an important relationship in a DC motor, which is a separately excited DC motor that we are talking about right now, where we are going to be able to adjust the speed versus a given torque by adjusting the armature resistance. Incidentally, some of the motors may not have separate excitation. Instead, they may have permanent magnet inside. That is as good as a separately excited DC motor, but with constant excitation. So if I have a small permanent magnet with north and south poles already, because of the magnetic material which is giving me a fixed amount of flux, that is essentially going to result in, the motor behaving very similar to a separately excited DC motor, but with constant excitation. In which case, I will also avoid IF square RF losses. There will not be any IF square RF losses. That is the major advantage. So I can say basically permanent magnet DC motor and separately excited DC motor both behave the same way. There is hardly any difference, except for the fact that I can't adjust the excitation. In separately excited DC motor, I can adjust the excitation. In a permanent magnet DC motor, I can't adjust the excitation. Right? So the next one we will be discussing, I'm just not going to immediately start discussing, but the next things that we will be discussing will be shunt DC motor, DC series motor, and we will also be looking at compound motor. So in compound, of course, we will be looking at differential and cumulative. Both we will be looking at, and then we will be deriving the speed torque characteristics for each of these motors. We will be deriving the speed torque characteristics or relationship for each of these motors. Okay?